Good evening. My name is Mariusz Dąbrowski. I'm the president of Jerzy Stelmach Eureka Foundation, which deals with interactive education and popularization of frontal scientific research. The foundation gathers active scientists, and therefore, for a couple of days, we offer you the lectures and the debates under the projects Science Closer to the Society. We are now at session 5 of this project, and the session is entitled Classical and Quantum Black Holes in the Universe. The project is co-financed by the Polish Ministry of Science and Higher Education under the program Social Responsibility of Science. And its aim is to bring the achievements of outstanding scientists to the general public. Our session will be held both in English and in Polish. There will be 3 lectures and 3 discussion sessions. English part, which is 1 lecture and 3 discussion sessions, will be translated into Polish and played later on YouTube in the period of 2 or 3 days after the session. Ladies and gentlemen, black holes and related objects in the universe are one of the most fascinating topics that bring together many threads that are considered crucial to the creation of the theory of quantum gravity. It is currently the most sought after theory in physics. The debate will aim to convey this fascination with the topic among scientists, to young people, and to the general public. Also, to outline the future practical application of this type of research. I am very pleased to announce that today's main lecture will be given by our guest, Professor Claus Kiefer from the University of Cologne, Germany. Hello, Professor Kiefer. Hello, Klaus.
Hello, Marius. Nice to see you.
Hello.
Hello.
Before we start the lecture, let me say a few words about the scientific career of our guest lecturer. Professor Kiefer is, first of all, a renowned quantum gravity and cosmology specialist, probably best known to the scientific community as an author of the textbook entitled Quantum Gravity, which was first edited in 2005. He also wrote a series of papers about classical and quantum cosmology and quantum gravity, the problem of time in cosmology, the theory of black holes, and the foundations of quantum theory in general. What is important also in the Polish context is that Professor Kiefer wrote a popular book entitled Quantum Cosmos, which was also published among other languages in Polish, and it's available under the title Kwantowy Kosmos. As for Professor Kiefer's scientific career, he studied physics and astronomy at the University of Heidelberg and also the University of Vienna. He defended his PhD in Heidelberg University in 1988. This thesis was supervised by Professor Dieter Zey, and it was devoted to the concept of time in quantum gravity. Very, very interesting and hard topic. Professor Kiefer then became a postdoc in Heidelberg, then University of Zurich, and also got a position of a lecturer at the University of Freiburg. And in 2001, he became a professor in theoretical physics at the University of Cologne, where he stayed until now. Professor Kiefer visited many places worldwide. Among them, he spent some longer periods at the University of Tours and the University of Montpellier, University of Cambridge, and Max Planck Institute, Albert Einstein Institute for Gravitational Physics in Potsdam. He also visited many places and attended a vast number of conferences, giving talks and seminars on quantum gravity and cosmology. In general, Professor Kiefer has written more than 150 research papers. They are cited more than 4,500 times, and the Hirsch index of these papers is H equals to 38, which means that 38 of his papers are cited more than 38 times. Last but not least, Professor Kiefer is my friend since 1996, when I first visited him in Freiburg University. We have written 2 papers on quantum string cosmology and quantum phantom cosmology together, and exchanged a lot of other ideas during the period of more than 20 years. Now, I think it's time to start the lecture. Professor Kiefer, Klaus, the screen is yours.
Yeah, thank you very much, Marius, for this kind introduction, also a kind invitation. It's of course a pleasure to see you again, in spite of not being in person, but from remote. I remember the kind invitations to Stettin many times before the pandemic. And but nevertheless, we can do by Zoom, and I try my best to give a general talk to the audience. So thank you again. The talk is about classical and quantum black holes in the universe, and of course there are 2 parts, namely the classical and the quantum. Just a brief remark, there are at some points are some mathematical equations. I do not intend that you all understand this. Please consider them as some kind of illustration. I think you should be able to follow the talk without the equations, but at some points it may be helpful for those who understand. Yeah, so I start historically in the 18th century. I mean, I talk about black holes, and at that time there were some ideas that resemble black holes, although the name was not coined yet. And the first, in my opinion, is John Mitchell in 1784 in Britain. I think he was also one of the first to measure the gravitational constant at that time. And at that time, of course, Newton's physics was prevalent, and Newton imagined light as consisting of corpuscles, of particles, so like any other particles. It was known in the 18th century that there is a finite speed of light. And so Mitchell thought, okay, if I have a star bigger and bigger, then of course gravity is stronger and stronger. And at some point, light that is moved outwards comes back because gravity is too strong, or in other words, it has a greater velocity. I mean, escape velocity is greater than the speed of light. And the quote is here from his paper. Hence, if the semi-diameter of a sphere of the same density with the sun were to exceed that of the sun in the proportion of 500 to 1, so it should be a star 500 times bigger than the sun, a body falling from an infinite height towards it would have acquired at its surface a greater velocity than that of light. It's just gravity is so strong that these light particles of Newton cannot escape. And consequently, supposing light to be attracted by the same force in proportion to its vis inertiae, so its inertial force with other bodies, all light emitted from such a body would be made to return towards it. So you cannot have light escaping from such a big star, but it would return by its own proper gravity. An independent prediction was made by the renowned French scientist, Pierre-Simon Laplace. But later, beginning of the 19th century, these ideas were abandoned because people thought that light is waves, only wave, and is not affected by gravity. So in his third edition of his book, Laplace omitted any reference to that. And it had a rebirth only in the 20th century, but from a very different angle. So we make a big jump to the 20th century, actually to the year 1915, when Albert Einstein um, accomplished his theory of gravity. It's called theory of general relativity. And it's no longer theory of forces that attracts bodies throughout the universe instantaneously. No, it's a theory about gravity as geometry. Locally, it's a geometric theory of gravity, no force anymore. And in this theory, also light is affected because if space-time is a geometry, everything, including light that propagates there, is affected by the curvature. Now you see here the Einstein field equations you do not have to understand. But just to mention in words, they have two sides, the left and the right-hand side. The left-hand side gives you the geometry of space-time, and the right-hand side gives you the particle energy content of matter. So, and these two are in interaction. So where there is energy or mass, space-time is curved. And where space-time is curved, I mean, the energy and the masses follow this curvature. So geometry and matter. And of course, you have to insert on the right-hand side everything that is known today. So the standard model of particle physics with all the electrons, quarks, and Higgs, and so on. Now, these equations are complicated, but nevertheless, they are exact solutions. And already very early, Karl Schwarzschild found a solution in 1916 that describes the geometry outside a spherically symmetric body, like the sun or like the earth or whatever. Vacuum, but outside a body. And in his honor, it's called Schwarzschild geometry. And here is a sketch. So Stern means star, sorry for that. And you have here where the star is, we have another solution, right? But outside you have this, looks like a trampoline, this curvature. So any light ray that comes is affected by this. Now Einstein and Rosen in the 1930s also found a solution that is called the Einstein-Rosen bridge, or you will see on the next slide, the wormhole. And this is when you do have always vacuum, so no star. So then you can construct a solution where you somehow enter a throat and reach another universe. So this is our universe, some hypothetical other universe, which is not present if there are stars. Yeah, so this is only a kind of academic solution, but people have reconsider this in the and interpret it as a wormhole. What is a wormhole? Okay, wormhole is a name. It has not to do with worms, but it has a structure similar to a real wormhole. So you have this upper part of the Schwarzschild solution here twice and connected through this throat. And so I call this here a black hole and white hole. Black hole means everything can go inside, but not emerge. So there's a one-sided entry. So gravity here is so strong that it cannot, and everything is thrown in, cannot emerge. And here you have the time reversal invariant, which is a white hole. So you can only get out, but not get in. We will see later that this is very hypothetical, but that this is actually seen. Now you can construct such a wormhole. It's a solution of Einstein equations, but if you want to use it for science fiction, I must warn you, it's not suitable for travel because of gravity is attractive. Even if you could construct such a wormhole, it would, due to its own gravity, collapse immediately. And this is why some people, especially in the United States in the 80s, thought about whether, yeah, there could be a wormhole that can be traveled through. And in fact, yeah, Kip Thorne, Nobel Prize winner Kip Thorne and others constructed this. Sorry, this means space-time, and this means the presence, and this means the future. You can construct such a wormhole if you have exotic energy that somehow have a repulsive force compensating the gravitational attraction. And then you could, if you have this exotic energy, you could stabilize it. So you could even then have a shortcut through space-time and use this as time machines. Now, this would be a separate talk, and I will not talk about time machines in my talk, but nevertheless, it's related. And even if it's only academic in the sense that we do not know such a hypothetical energy, such his hypothetical exotic matter, it's a solution of Einstein equations. And so at least in principle, it's something that could be real. Now let us go to the what we go to the observable black hole, so collapse to a black hole. So typically a collapse, if a star collapses under its own gravity, it can result in three endpoints. I mean, if the mass is not too high, it can become a so-called white dwarf. This is the fate that our sun will experience in a couple of billion years. If gravity is stronger, say 3 solar masses and higher, it could become a neutron star. So very compact, dense object basically consisting of newtons. But if the mass is further increased and maybe beyond 5 or 6 solar masses, then nothing can compensate the gravitational collapse, and the object somehow condenses to what we call a singularity, a hypothetical space-time region where matter, in a sense, is squeezed out of space-time. And this is here sketched here. So the time and space is here two-dimensional. So we have the stellar surface, and which collapses. And once a certain limit is reached, and this limit is called Schwarzschild radius, it depends on the mass. 2 times the gravitational constant times the mass over speed of light squared. And if everything is inside that, nothing anymore can escape. You can, if you're, this shows light cones. So if you're outside, you can send light to your relatives far away, and you can send light here. But if you're inside, you see light can only be sent here along this cone, and this is tilted towards the inner. So even if you try to send a message outside, it will rebend and end up here in this final singularity, which is a region where space-time is no longer defined and where matter densities become infinite. So this is the apparent, this is the event horizon. So once you cross this point of no return, I mean, there is no hope. So you can never ever send any signals outside. And this singularity actually is a region in time, a point in time, because I mean, Einstein's theory is about space-time, but it can have very counterintuitive properties. So in the interior of a black hole, which means interior of the event horizon, time and space can exchange its character. So what originally was space now, which is the central point of singularity, now is a point in time. And this is why you cannot avoid it. Yeah, you can never avoid a time point. You cannot circumvent it. So you cannot see it in front. It's in your future only once you reach it, but that's the end. So the metaphor here is, okay, out of space now becomes time. And okay, black holes have been observed, and I tell you some examples. A very impressive one is the one that is connected to the first direct detection of gravitational waves, which happened in September 2015, so roughly 100 years after Einstein had predicted gravitational waves. And so this is a picture from the LIGO group, who the interferometers who measure it. I will not discuss the interferometer, but it was clear from Einstein's theory that the measured gravitational waves, they come from black holes, from two black holes that circle around each other in a cosmic distance, so very, very far away, and then melt to one black hole. And in this process of melting, they emit gravitational waves. So gravitational waves are disturbances in the structure of space-time that propagate with the speed of light. And since this was in cosmic distances, it took millions of years to reach us. So we saw an event that happened millions of years ago in the universe, and we could actually reconstruct the masses and the dynamics of these black holes from these signals. So this was certainly, I would say, one of the biggest triumphs in the last 10 years in this field. And Gibson and others, they got a Nobel Prize for this. Now, we distinguish black holes according to their mass. So there are lighter ones and heavier ones. And so here this slide is about stellar mass black holes, which are black holes have a mass of stars, maybe 10 solar masses, but even more. So one has found that these gravitational waves, they came from merging two black holes with masses around 35 and 30 times the mass of the sun. So that's already at the higher edge of stellar mass black holes. So they merged, and it resulted in a black hole with mass around 62 solar masses. So, okay, if you add 30 and 35, you think, aha, 65. So did the speaker here made an error? No, 3 solar masses were entirely radiated away in form of energy as gravitational waves. No? According to Einstein, E is mc squared, so energy is mass times c squared, and that much in mass was radiated away in energy. So that's absolutely impressive. Many other stellar mass black holes have been indirectly observed. Like there's a whole list that you can find in the internet. Here I have one example called V404 Cygni. So this refers to the constellation of Cygnus, and this is variable stars with around 9 solar masses. So this is definitely a black hole. It's a binary system where the black hole has a companion star, an ordinary star, and because the black hole attracts so much matter from the ordinary star, matter goes over to the black hole and circles around it because of angular momentum, forms a so-called accretion disk, and heats up due to friction. And what you observe in many cases is X-rays. X-rays. So you don't see the black hole directly because it's black, but you see its influence, its gravitational influence on the neighborhood. And there's a whole list of such black holes already. Now there are the stellar mass black holes, but there are also the so-called supermassive black holes. And these are very, very heavy black holes, which have not 10 or 100 solar masses, but millions and billions. And in 2019, an impressive result was published from the so-called Event Horizon Telescope collaboration with radio telescopes. And this is by itself an interesting story. But what was found was that in a galaxy, and the galaxy has the name M87, there's a central black hole with a huge mass of 6.5 times 10 to the 9, which is a billion solar masses. And you see here, well, it's not meant literally, but with some image processing, the event horizon, or at least the horizon of a black hole and the matter around it. We believe that in practically every center of of every galaxy, there is a supermassive black hole. And of course, the closest is the one of our own galaxy, our Milky Way. And this is called the galactic black hole. And this is a picture that the same collaboration published in 2022. And so this has a certain name because Sagittarius, this is the constellation where this is seen, has a mass of 4 million solar masses. So not billion, but million. And we believe that these supermassive black holes lurk inside the centers of every galaxy. There's a dispute in astrophysics about the intermediate mass range between stellar mass and supermassive black holes. This is not yet decided, so we have definite evidence for stellar mass black holes and definite for supermassive, but the in-between is not so clear. Now, is that the end of the story? Einstein's theory has predicted these no return objects, these collapsed objects, and can describe it, and we have observed it. These black holes are characterized by this horizon, and inside is a singularity. So there could be situations with more complicated solutions where the horizon is absent and where you could see directly the singularity. But this would be, of course, a disaster for physics, because if you have a singularity, everything could come out and you would have loss of predictability. This is why Roger Penrose, the Oxford mathematician, in 1969 came up with a hypothesis, namely that in a realistic gravitational collapse, I mean, no symmetry assumptions, an event horizon forms which prevents the singularity to be seen from the outside. So we call it also nature abhors naked singularity. So all singularities are at rest, you cannot see them. There are counterexamples to this, but they are not generic, they're not realistic. So it seems that this is correct, but no proof is available. It seems that at least in realistic situations, you have these event horizons. Now, black holes are, you may think they are very complicated because you have to solve Einstein's equations, and these are highly complicated things. This is, on one hand, it's true, but on the other hand, it turns out that they are very simple, that they are much simpler than maybe stars. When a star has many properties, so many billions and billions of particles and temperature. Black holes more or less look all the same. John Wheeler, I should have said John Wheeler also coined the name black hole in the 1960s for these objects that don't allow to escape anything from the in to the outside. John Wheeler called it no-hair theorem. Now, strictly speaking, it's a three-hair theorem, because the theorem, which is a mathematical theorem without many assumptions, states that there are just 3 numbers that fully characterize a black hole. And so it says that stationary black holes, these are the ones that occur at the end result of the collapse. And if you just use general relativity together with electrodynamics, this is what is meant with Einstein-Maxwell, then 3 parameters fully characterize any black hole in the universe. All the ones that you have seen in my examples and all others, namely the mass, I mean, how heavy it is, then how fast it spins, the angular momentum, and if it has an electric charge, then this you have to add. We don't believe in astrophysics that black holes have a charge. We think they are neutral because we have positive and negative charges in the universe, but mathematically it's possible. If you have really all the 3, then you do no longer have the Schwarzschild solution, which only has mass and is spherically symmetric. You have a solution that is axial symmetric, and it's called Kerr-Newman solution, after the 2 mathematicians, physicists, Kerr and Newman. In astrophysics, charge, as I said, is supposed to be irrelevant, and there it's the Kerr solution. The New Zealandish mathematician Kerr in 1963 found this solution, which is supposed to be the most important solution for astrophysics. And it has, okay, I will make here a mistake. I just see it's completely characterized by the mass and by the angular momentum. Sorry, sometimes you see mistakes only when you look at your slides. So only M and J. And the examples you saw, for example, the one with gravitational waves, they are characterized by their mass. This is the 62 end result of solar masses, and one can also derive the spin, the angular momentum. Now, okay, black holes seem to be very simple. Um, and nevertheless, they seem to have a nice analogy with thermodynamics. So thermodynamics that you study when you look into gases and bodies and heat up something and study the weather or whatever. There are analogies between the laws of thermodynamics and the laws of the black holes. And of course, you know from thermodynamics, there's an important quantity called temperature, which is constant if you have an equilibrium, so no longer mixing between two gases. And this temperature is analogous to what is called surface gravity. This is a measure of the force with which the black hole attracts bodies. In thermodynamics, you also have what is called entropy. This is, I mean, you usually hear about entropy as a measure of order and disorder. So if you increase disorder, then entropy increases. This is what happens with all of us every day when in our room we do not take care of the order of things, and things get disordered. And this entropy, which is supposed to either stay constant or to grow, is analogous to the area of the black hole. And the area is really the area of this event horizon. Yeah, the event horizon distinguishes the inside from which nothing can escape to the outside. Now, originally, people found that around 1970, and they thought this is just an analogy, but black holes has nothing to do with temperature. So how come? Well, if it were more than just an analogy, one can see in equations that a new length scale should be there, a length scale, a fundamental length scale that is not there in Einstein's theory. Now, the only candidate is the so-called Planck length, and this opens now the door a little bit to the second part of my talk, I mean to the quantum part, namely the Planck length. This results from a combination of the gravitational constant, which gives you the force of gravity and the speed of light, but also Planck's constant, which is a quantum of action, which we call h or h bar, and which rules quantum mechanics and rules the microscopic constitution of matter. Now, in Einstein's theory, there is no such Planck length, but if you somehow bring in the quantum of action, then you could construct. And it's called in honor of Max Planck, who already introduced this in 1899 at the Prussian Academy in Berlin, actually before officially announcing Planck's constant. He saw that just from experimental results, there should be a new constant of nature. And this is what later was called Planck's constant. And if you take this together with G and C, then you can really form fundamental units. And these are the famous Planck units that you can already find in Planck's paper, but this is the modern notation. So you have Planck length, Planck's time, Planck mass, and you see here the combination square root of Planck's constant, G and C cube. And numerically, this is very small. I mean, 10 to the minus 35 meters means 0.000, and only at the 35th entry comes a 1. So we cannot see such very small scales. I mean, we can see at accelerators, for example, in CERN, Geneva, maybe up to 10 to the minus 18 or so meters, but not that. But nevertheless, Planck predicts that if you combine this, there's something important should happen at that scale. The Planck time is the time that light takes to propagate the Planck length. And of course, this is very, very short, 10 to the minus 44 second, much, much shorter than any time scale than we can resolve, which is maybe around 10 to the minus 18 seconds. The Planck mass seems to be more every day, 10 to the minus 8 kilogram. That's something you find around you. But if you translate it into units that the particle physics physicists used, and they like to use these electron volts or giga electron volts, it's very huge. Maybe you don't understand this number, but it means that this is 10 to the 19, so 1 with 19 zero times the mass of the proton, out of which we also consist. And so we cannot have energy to create such particle. I mean, you would have to increase the accelerator at CERN, I mean, to galactic dimensions to create a Planck mass particle. And I think I can say that for financial reasons, that will not be possible. Now, Planck in 1899, he finishes his paper with writing here in the translation, these quantities, so these, retain their natural meaning as long as the laws of gravity, of light propagation in vacuum, and the two laws of the theory of heat remain valid. They must therefore, if measured in various ways by all kinds of intelligent beings, always turn out to be the same. So already from these preliminary results of the theory of heat, he could deduce such a unit and suggest that they can be used as a universal unit. So if you contact extraterrestrials, of course, they don't use meters or whatever, seconds, but they could also construct these Planck units. So you could use them really as universal units. Now, back to the black holes. I just said the black holes have this no-hair theorem, have just these 3 or 2 numbers, and that they look a bit like thermodynamics. So now comes the most famous result in this context, I mean, the result by Stephen Hawking from 1974. He found that actually this is more than an analogy. He found that black holes should really radiate with a certain temperature. This has to do with really using quantum theory on the background of a collapsing body and to go beyond just pure Einstein, because the Planck's constant, the quantum mechanical quantum of action, is not contained in Einstein's theory. And he found black holes should radiate with a temperature proportional to h bar. And it's in his honor called Hawking temperature. And here you have the black hole temperature, which has for a spherically symmetric black hole, a Schwarzschild black hole, this expression. So you see h bar occurs, speed of light, 8 pi is the number, gravitational constant, this is Boltzmann's constant, we shall return to Boltzmann, and the mass of the black hole. So except for these units, it's proportional to 1 over mass. That means the bigger the mass is, the smaller is the temperature. So very big black holes, you cannot really see the radiation, and you see here the numbers. This means solar mass over mass. If the black hole is of a had, I mean, it should be a bit bigger, but had a solar mass, then only you would have 10 to the minus 8 Kelvin. So this is almost close to 0 Kelvin. And if you go to the universe, you have this 3 Kelvin microwave background radiation, which is much bigger than that. So much more goes inside the black hole than is radiated. So you would need really very small black holes to see the temperature. And these are called primordial black holes because they cannot be created from stars. They should coming from the early universe and maybe very small masses like crumbs. There is a search for them, but so far none has been detected. I will tell you again later, because they radiate, they lose energy, and once everything is radiated, then the evaporation stops, and the radiation is over, the black hole has disappeared, so they have a finite lifetime. One of the most prominent black holes, for example, again in the constellation Cygnus, for example, evaporates after 10 to the 68 years. Now, that's much too long to wait for any project, because this is 10 to the 58 times the present age of the universe. Yeah, so this is why today we don't see evaporating black holes, because our universe is much too young for this time. We would have to wait much, much longer. There's an analogy of this even without gravity in flat space-time. So if you in gravity, I should mention this. There's a relation between gravity and acceleration. Locally, gravity and acceleration are the same. As you see, when, for example, when you are in a small lift, that whether it stands on Earth, you feel gravity, but if it's in empty space, just accelerated, then due to the inertia, you stand on it just like on Earth. And this is why a similar effect already exists in flat space-time. And this was found in 1976, basically by Bill Unruh, and it's called the Unruh or Davis-Unruh temperature, which is again proportional to h bar, and now the acceleration, yeah, the linear acceleration of the observer. Okay, this is just a diagram, a two-dimensional diagram, time and space, and this is the light cone, and with constant acceleration, you are here on this hyperbola, and this then has features similar to the interior of a black hole. So if you're here, then you cannot send information to this accelerate observer. This is why some features in this acceleration context are the same as in the black hole context, but there's no singularity here. Now, and if you stop accelerating, you can, of course, see everything. Now, this temperature is very small. I mean, if you measure A in meters per second squared, then you have 10 to the minus 25 Kelvin. People try to measure this with lasers. But so far, to my knowledge, it was not clearly seen. But it's certainly possible to have these effects measured in the laboratory. And this would also give more credit to the Hawking effect, which we cannot so far directly see. Now, I already said black holes have a finite lifetime, and if you measure the initial mass and solar mass, it's 10 to the 67 years. We cannot imagine that. Now, our universe is only 10 to the 10 years, and I mean, this is immensely much bigger, so we cannot imagine a world with that. So for the observed black holes, this is much bigger than the age of the universe. Now, when Hawking had a black hole collapsing in a space-time where also quantum fields are there, and the quantum fields, quantum mechanics causes this Hawking radiation. But he used an approximation, namely gravity was still classical. Yeah, so gravity itself was not quantum, only the rest. But his approximation breaks down when the black hole that radiates and becomes smaller and smaller when it approaches the Planck mass, because then, as we have seen, gravity and quantum simultaneously play a role. So if after the black hole evaporation, and if this is over, only thermal radiation remains, which is under dispute, then you would also have the problem of information loss, because whatever you start with, maybe a star or other object, you always end with the same radiation. Yeah, but this is found in Hawking's approximation, and I will show you there are disputes about whether this is fundamentally correct. Now, if black holes have a temperature, so they radiate, they also must have an entropy. And one can calculate this entropy by standard thermodynamical calculations. And there's a famous result that goes back to maybe first Bekenstein, but also then Hawking. And so you could read BH as Bekenstein, Hawking, or black hole. So you have the area of the event horizon, speed of light, h bar and t. And if you remember the Planck lengths, then you can write this. Now, this is just Boltzmann's constant. It gives the correct dimensions. But the important thing is this. So you measure the area of the event horizon in units of Planck length squared. And this is a picture I modified a bit from what I learned from John Wheeler, or what he also published, so that we have the event horizon and have small Planck length squares cells where we put ones and zero on it. So that's the number of ways you can put bits on this. And okay, you can give the numbers. Maybe this is not so intuitive to you, but for a mass equal to the mass of the sun, you have a huge number here. I mean, the entropy of the sun, if you just count the particles, it's 10 to the 57, which is 20 orders of magnitude. So forming a black hole, I mean, no one of us can make such big disorder in terms of entropy than that. I mean, we can try our best to make disorder in our room, but this amount of disorder you cannot reach. So 20 orders of magnitude. So really, black holes seem to be a huge swallower of information. Now, is information really lost? Hawking originally thought, yes, it's lost. But later he changed his mind. I remember 2004 at a conference in Dublin, he announced that he changed his mind. And I think this is now the majority opinion. Okay, you can say information is indeed lost because you have a new physical theory and radiation is always thermal. But what most people believed is that information is preserved, but you have to go to a more fundamental theory, a theory of quantum gravity, where gravity is also quantum, to see that. Hawking's approximation, which leaves gravity classical, cannot see it. There's also a third opinion that there is no complete evaporation, and that the black hole leaves a relic. This has had some popularity in the past, but it doesn't seem to be as popular now. Now, how can we decide? There are many papers on that, but I think the final answer can only come from a theory of quantum gravity. Um, I remember well when we discussed this at a conference in Stockholm in August 2015. So Hawking also gave a talk and had some new ideas how to preserve information. Okay, I was also there, but you see also de Hooft and Charles Meissner and many others. And this conference still showed that, I mean, there is a dispute. I mean, this is not something that has been settled, and there are different opinions. And Hawking at that time, his opinion, his new model had some influence, but I think it's not, it has not fulfilled its promises as it was stated in 2015. Now again, you see Hawking and Penrose now here in younger years. Quantum gravity. I should at the end say, of course, something about quantum gravity. And these two gentlemen have proven in 1970 that actually Einstein's theory is not complete. My Newton's theory is also not complete, but you cannot prove it directly from Newton's equations. But here, under some assumptions like energy rules, you can show that Einstein's theory is not complete. It cannot describe the beginning of the universe, the Big Bang, which I haven't told about, also not the interior of black holes, so the singularity theorems. So are there really singularities, or what happens? I mean, singularities for physicists means that's the end of predictability. So we believe there's a more fundamental theory without singularities. But we do not yet know, although there are models. Now, the open problems that we would like to address that a theory of quantum gravity should solve for us for black holes are the following. Okay, Hawking, we believe in Hawking's formula, a black hole radiates, it emits approximately thermal radiation, and it shrinks and shrinks, mass becomes smaller and smaller until the Planck mass of 10 to the minus 8 kilo. But after that, his approximation breaks down, and yeah, we do not yet know the final phase. And of course, a theory of quantum gravity should explain it and also what we see then in observations. Also about the fate of the classical singularity in the interior. It should also give us some understanding of entropy. And important is, yeah, do primordial black holes exist? I mean, black holes with very small masses. There's a search for such black hole, but nothing at least nothing definite has come out. Some people think there's planet X around the sun, which is not really a planet, but it's a primordial black hole of grapefruit size. But I cannot judge how serious this is. But some people discuss this. Now, for the microscopic interpretation of entropy, I mean, this person, Ludwig Boltzmann from Vienna of the 19th century, is very important because he laid the foundations of modern thermodynamics, which does not just deal with temperatures and pressure and volume, but with the microscopic interpretation. And he could show that, in fact, all what we know about heat and the like, thermodynamics comes from the mechanics of very small atoms and molecules. Of course, many people at the time did not like it and attacked him very strongly because they did not believe in atom and so on. But time has shown that, I mean, the world consists of atom and molecules, and that Boltzmann was correct. So in his interpretation, the total energy of a gas is the sum of all these particle energies. The temperature is defined just by the average energy of a particle. Yeah, and the entropy, this is of course the most subtle, but maybe also the most central quantity. The entropy, which is the measure of disorder, gives the number of possible microstates, possible states of atoms and molecules for given macroscopic appearance. So you have a gas, it has a temperature, a volume, pressure, energy. You don't see the microscopic particles. You don't see the atoms and molecules, but they are behind. And if you count the number of ways of their possible location and motion, that are consistent with this temperature on, then you get the entropy. And Boltzmann then has this formula that it's the logarithm of the probability. So probability did enter here for the first time, I would say, in physics at a fundamental level. And later in quantum mechanics, it was even more fundamental, but already here, probability. So there's a difference between a probable and an improbable state. And the famous second law of thermodynamics tells you that the entropy, if left alone a system, if you don't enter it, if it's closed, then it always has a transition from an improbable to a more probable state. So order decreases. Now here again, you have this picture with the bit. And so Boltzmann had these atoms and molecules. And in gravity, we would imagine that somehow bits are related to the event horizon of a black hole. But the details, of course, depend on the theory. Now, of course, I could tell you many things about quantum gravity. So far, this is a theory in construction, and also my time, I think, is approaching the end. So only briefly, what are the main approaches to quantum gravity? John Wheeler once wrote, no question about quantum gravity is more difficult than the question, what is the question? So what is the correct approach? And if you look into the literature, we have various approaches. So many just take Einstein's theory and try to make a quantum version out of it. They go under the name of path integrals or geometrodynamics, loops, and others. There's also string theory that starts from something totally different. A new theory and quantum theory of everything, out of which then quantum gravity emerges in a limit. And there are also other approaches which time does not allow me to discuss, which start from a discrete structure of space-time. And all of these approaches say something to these questions. So to entropy, to black hole radiation, to singularity avoidance. For example, to the question about the microscopic explanation of entropy, which is this famous formula that the entropy of black hole is the area in terms of 4 times Planck length squared. There's a theory called loop quantum gravity, and this has a precise idea about microscopic degrees of freedom, like Boltzmann's atoms. In this case, they're called spin networks, and they count these spin networks, and under certain assumptions, which I have no time to enter in the discussion sessions on the other days, I can tell more, but they count it and find at least this proportionality to the area. String theory also is able to do that, but not for the Schwarzschild black hole, but for more exotic string black holes. They found this formula. And also this geometrodynamics that I mentioned, you can find this proportionality, but so far not with the correct factor. So you see many physicists, they work on this and try to attack this from different angles, but it's very hard. Now, the last topic is about the direction of time in the universe and its relation to black holes. And okay, this is a metaphor, a painting by Paul Cézanne about still life that shows you, I mean, the working of the second law that, of course, there is a past, present, and future, and entropy increases to the future, and also order decreases, no, as you see here in these objects. Now, let's jump at the end to our universe as a whole. And Penrose, again, he estimated some time ago how likely our universe is. When he talks about the universe, or we mean the observable part of the universe. The universe may be much bigger, but I talk here about the part that we can observe. And Penrose estimated that the entropy is maximal when all the mass is in one gigantic black hole. So, of course, the universe has black holes, has other objects, but if you, in your mind, had everything in one black hole, then because black hole has such a huge entropy, it would be the most probable state of the universe. Okay, this is, Penrose likes to jonglate around with numbers. I mean, this is just, I mean, the probability of our universe, and this is the maximal probability. And he has huge numbers that, I mean, maybe is difficult to grasp intuitively, but what he gets is a very small number of our universe. Now, he says we are so far apart from the maximal probability from everything is in a black hole that there should be a reason behind that. It's not just by accident. Yeah, so even if we think about the probability that everything now suddenly emerges out of nothing by a fluctuation, even I and you and our memory, then this is amazingly small, but still bigger than that number. No? So to understand the universe, it seems we have to really find a fundamental theory. And Penrose in 1979, he had this picture. At that time, it was popular to have a universe that expands and recollapses, has a big bang and a big crunch. And he says, okay, the Big Bang was very special, so very low entropy, because high entropy means more and more black holes. And so the Big Crunch is like here with stalactites, black holes have very high entropy. He formulated it, he used so-called wild tensor hypothesis, but it was just a suggestion. What we contributed to that some time ago was in quantum cosmology, when you also quantize the universe, the picture is different because Big Bang and Big Crunch are no longer distinguishable in quantum cosmology. They are just regions of very small size. And so if you have a very small entropy here, you should have a very small entropy here, because both are radius 0, and Big Bang and Big Crunch are just classical concepts. Now, this is a very weird picture, it seems, because it would mean that if we expand here, entropy increases, but then it would decrease again to radius 0. So then, I mean, if we have a glass that falls down and breaks, would then re-emerge? No, this would hold for all observers. And so, which would mean that the classical world here would come to an end, and that the hypothetical other observers would here observe the same, namely increase of entropy here. This is a speculation, I admit, but it's a solid speculation in the sense that it's based on concrete equations of quantum gravity. That may be wrong at the end, but that may seem very natural right now. Now I come to the end here. And let me summarize. The talk was about black holes, and was mainly about black holes in Einstein's theory of general relativity, that it's it's a straightforward prediction of that theory. And that it's not only on equations and on paper, but it's observational support for black holes. We have many candidates for stellar mass black holes and for supermassive black holes. And it's a flourishing field of investigation in astrophysics. There may also be primordial black holes coming from the early universe with very small mass, and we would like to have them because then we could test Hawking radiation, but so far none has been detected. I emphasize black holes, which seem to be something classical coming out of collapsing stars and Einstein's theory, but they're also quantum objects. This is what Bekenstein and Hawking here brought into the game. They emit radiation and they have an entropy. So they have properties like our gases in the room, although a bit in a strange way because they radiate, but they become smaller and less mass, but the mass is in the denominator, so they become hotter upon radiation. No? Our hot tea will become cooler, of course, colder, but they hotter, and they have a finite lifetime, which is very long, too long to be seen for the stellar mass black holes. But this final evaporation could be seen for the primordial black holes, but we need a theory of quantum gravity to describe it. Now, in quantum gravity, we expect that black holes have no singularity, and many models point to that. In one of the papers with Mariusz that he kindly mentioned was devoted to that, and we could show in a model that there is a singularity-free beginning of the universe. It was not about black hole, it was about cosmology. And then there's, of course, no problem with cosmic censorship or information loss because then there are no singularities, so we don't have to worry about this. So these are fascinating topics that are under current research where I and colleagues work on. But at least there are concrete models in certain examples where the singularities are avoided. Yeah, this is the last slide. Of course, there's a huge literature. I still like this book by Kip Thorne, the Nobel Prize winner, very much, which is a popular, semi-popular book, Black Holes and Time Warps. It's probably available in Polish also. I'm not sure. And Mariusz kindly mentioned also my book that was translated to Polish, Kwantowy Kosmos, which is about not only black holes, but about the universe also. And Michael Heller, a very distinguished colleague from Krakow, whom I visited many times, he contributed here this motto for the book on the cover. And with this motto, I would like to conclude and thank you again for your attention and for your patience.
Thank you very much, Klaus. It was a very nice talk. I think that our audience will have a lot of benefit from that. I would like to mention one topic about the time travels. I think that I could refer the audience to my talk, which was given on the 19th of March 2021. It was from calendar to the time travels. It's YouTube. It's in Polish, but it's available on YouTube. So if somebody wants to explore more, please just have a look onto this.
Thank you.
Now I would like to thank Klaus for this very good talk. And I would like also our audience to listen to us. Tomorrow there will be a talk by me about some exotic many-dimensional objects in the universe. And then I would like to invite also on the lecture by Professor Marek Biesiada on Friday about the observations of the black holes in the universe, and into our discussion sessions in which me Professor Kiefer, Professor Biesiada, and Professor Zalzano will explore in more details the issues mentioned already during today's lecture. And the discussion sessions will start on Friday at 12 and then 1:30. And then there will be the summarizing session on Saturday at 11. So I would like to remind our audience that this program is co-financed by the Polish Ministry of Science and Higher Education under the program of Social Responsibility of Science. And please visit our website on YouTube, www.youtube.com, just Fundacja Eureka. You will see this talk and as well as many other talks which have been performed. So thank you very much. Thank you, Klaus. Thank you, our audience, both on Zoom and YouTube, for participation. And please come tomorrow, Friday, and Saturday. Thank you very much and good evening.
Yeah, thank you very much again and see you in the discussion sessions. And I'm also willing to answer questions then. So thank you again and have a good night.
Good night.
Good night.